Hello, everyone. I'm Peter Kish from the University of Warwick, and I'll be presenting our paper, Near Optimal Dynamic Rounding or Fractional Matchings in Bipartite Graphs, which I co-authored with Shayan Bhattacharya, my supervisor, Aaron Sitford from Stanford University, and David Weitz from Technion. So let's briefly talk about our paper, the setting we're considering, the problem. We will talk about dynamic matching. In this problem, we are given a graph undergoing edge insertions and deletions, and our goal is to maintain an alpha approximate matching. If mu of g stands for the maximum matching size, m is defined to be alpha approximate if size of m times alpha is greater or equal than mu of g, so alpha will be greater or equal than 1. For example, this would be a 3/2 approximate matching on the right, and our goal is to maintain such a matching throughout this set of updates, and our objective is to minimize the update time it takes us to maintain this structure. We talk a lot about fractional matchings, so let's just define them quickly. A fractional matching is a weight assignment to the edges between 0 and 1, or a vector over the edges, which satisfies that the sum of the weight of the edges incident on any vertex is at most 1. That is, can be thought of as the fractional linear programming relaxation of matchings, something like this one here. And it is known that the integrality gap is 1 for bipartite and 3/2 for 3/2 for non-bipartite graphs, meaning that the maximum matching and fractional matching size in bipartite graphs is the same, but in non-bipartite graphs, fractional matching size might be 3/2 as much as the integral matching size. If you think of a triangle, this is straightforward to see. So let's briefly talk about a very successful template for integral dynamic matching algorithms, and this is dynamic rounding. So it involves 2 steps. In step 1, the algorithms maintain a large fractional matching instead of an integral one. The intuition why this might be easier is because if you manage to do this in such a way that the fractional weights of edges are tiny, then updates happening to the graph don't change the fractional matching much. It's just more robust and can handle more updates. And in a second step, they round this fractional matching to integral, and they output this integral matching as their solution. So this framework defines the problem of dynamic rounding of fractional matchings our paper is focusing on. And what this problem is that given some fractional matching W on a graph G which undergoes edge updates, our goal is to maintain the matching M on the support of this fractional matching W. The support is just defined to be the non-zero edges of W, such that the size of M is at least the size of, is 1 plus epsilon approximate with respect to the size of this fractional matching. And note that this can always be done for bipartite graphs, right? So let's just briefly mention prior work on the dynamic matching problem. It is a well-studied problem. The set of papers mentioned here is far from being exhaustive, and solution can be put in 3 categories. There are a lot of papers focusing on 2 plus epsilon approximate dynamic matching in polylogarithmic update time, which is the best one can hope for in the dynamic regime. There's a set of papers focusing on 2 minus delta approximation for some absolute constant delta in poly n update time. And more recently, there have been papers which achieve 2 minus delta approximation for some absolute delta in polylog n update time, but these algorithms only maintain an estimation to the size of the maximum matching and not the matching itself. So where does dynamic rounding becomes useful amongst these set of problems? Well, in the fully dynamic case, where both edge insertions and deletions happen, dynamic rounding has been used in algorithms which maintain 2 plus epsilon approximations in polylogarithmic update time, and 2 minus delta approximations in arbitrary small polynomial update time depending on delta. And for the decremental case, where only deletions happen to edge deletions happen to the graph, 1 plus epsilon approximation algorithms with polylog update time also use the dynamic rounding framework. So let's briefly talk about prior rounding frameworks and where our solution will differ from them. They look roughly like this. So on the right, there's some dynamic fractional matching. In first step, these previous algorithms took this fractional matching W and maintained a sparsifier on the support of W dash. such that this parsifier fractional matching roughly had the same size as W, but it satisfies that it has a small number of edges, or it just has small maximum degree, something like polylog n over epsilon. And in step 2, completely ignoring the fractional structure of W dash, they use an integral matching algorithm on W dash and maintain a large matching on the support of W dash. And using standard algorithms from literature, this can be done in delta W dash over epsilon square update time, where delta W dash stands for the maximum degree of W dash. So while this works successfully, what issues does it propose? Well, it is certainly slow. So step 1 itself, this parsification step for using algorithms in literature takes polylog n over poly epsilon update time. This parsifier received at the end of step 1 also has some maximum degree with hiding similar factors. And step 2, the rounding of W dash with ignoring its internal fractional structure also adds 2 epsilon factors using state-of-the-art algorithms. Our contribution is in improving on these frameworks. To put it numerically, we give dynamic fractional matching rounding algorithms with different update times for different settings. If we want the algorithm to be deterministic, we can show it can be done with update time roughly log n over epsilon. Prior algorithms had update times roughly log n to the 4 to epsilon to the 6, although these are not clearly stated in those papers. We can show algorithms which are randomized against an adaptive adversary in log n square over epsilon update time. Now, an adaptive adversary is defined to be an adversary which is aware of our internal random bits. That is, updates happening might depend on not just previous updates, but whatever algorithms have chosen to do and how it managed to generate its randomness. And this concept of adaptive adversary is important for dynamic algorithm design. Is dynamic algorithms are very often used as dynamic data structures, where future updates happening to the data structure itself might depend on the state it takes based on previous updates. Such algorithms all had update time at least 1 over epsilon to the 4th in literature. And notably, we show randomized algorithms against an output adaptive adversary, which is a slightly weaker notion of an adversary who is not aware of our internal bits, but is only aware of our output at a given time. This algorithm will run in update time until the 1 over epsilon, that is an update time which is completely independent of log n, and it's roughly optimal. And note that for most applications, this notion of weaker adaptivity is sufficient, and prior works have not really considered this notion of adaptive adversary the same bands of 1 over epsilon to the 4th stand for it in literature. So what is different in our approach? Well, in the main difference is that we avoid step 2, that is, we avoid the step where we completely ignore the structure of the fractional matching we are given and use an integral matching algorithm on it. Essentially, we directly round without having this substep, and we also make the sparsification step near optimal. So how do we directly round the dynamic fractional matching? Let's just take some fractional matching, and we will first go through a static algorithm rounding it. So let's take this fractional matching and look at the binary decomposition of the fractional weights. And let's define EI to be the set of edges which have one at the ith binary bit of their weight. Note that EI now defines a multigraph. Our algorithm will go as follows. We'll start with EK for the largest, so smallest bit we are considering. We'll talk about that later. Say E3 in this example, 1 over 8. We define the supporting set FK. And for I, running from K to 0, we will look at the union of EI union FI, this supporting set we have, and all the edges with 1 at the ith binary bit. We split it in roughly 2 equal sets with an operation called degree split. I will talk about it in more detail. Something like this. And then we define the next supporting set, the supporting set of the next layer, Fi minus 1, to be the larger of these 2 splits. So in this example, say the purple edge set. And the intuition here is that we will be able to add the weights of the edges dropped in the previous layer to fi minus 1. So something like this. So that we repeat this as I goes to 0, and we'll just simply output E0 union F0, and now it, by definition, it will be an integral matching. So let's just briefly talk about what this degree split step does. For this, we don't claim novelty. This has been used previously in literature. Given some set of edges H, we want to generate another set of, we want to decompose this set H into H1 and H2, such that H1 and H2 are roughly the same in size, that they're almost exactly the same up to rounding. But not only that, from every vertices perspective, they are the same. That is, every vertices degree is roughly the same in these two sets up until rounding. And this can be done in linear time using methods from literature by taking every other edge in a maximal walk decomposition. So let's briefly talk about how we analyze this algorithm. Well, the correctness will follow from the following logic. In each iteration, we will take E0 union F0, and we will roughly split them. So any edge weight we assign to E0 union F0 edges, once we split them, we can double it and maintain validity throughout the graph. Since each of these degree split subreturns will run in time roughly linear with respect to the edge set, this whole process will run in roughly time. The straightforward upper band for the running time of this whole process is roughly k times the size of the edge set. How do we make it dynamic? Well, we will just say that as long as not a lot of updates happen to any of these layers, EI, then we will be able to say that the output roughly stays correct. We will be able, not a lot of updates happen will be defined by a multiplicative fraction of epsilon over k. So summing over all k layers, it adds up to just some epsilon error. And on a high level, we just rebuild whenever this error gets too much on one level and rebuild the data structure from that level upwards. What update time will this give us? Well, let's just for sake of simplicity assume that there's a single layer EK. Building this whole structure will take us time roughly k times size of EK. And each rebuild, we will rebuild every time the size of AK times epsilon over k updates happen. So the update time will be roughly k squared over epsilon. So now we have to talk about what k is here. So which binary bit do we start from? Well, to begin with, we may ignore very tiny edges, which just can't add up to too much weight over the whole graph. So say if we ignore every edge with weight less than epsilon over n squared, these might add up to at most epsilon weight over the whole graph. So that is fine. However, this requires us to set k to be roughly log n, which will turn into log square in update time. As I promised to you, we are presenting algorithms which are a lot faster than this. So how can we go about this? The idea is to do the same thing as other papers did before us. That is, we first sparsify these small weight edges of the graph, but unlike them, we sparsify these with a different technique, a slightly different sparsification technique. And with this sparsification technique, we raise the edge weights we are considering from 1 over poly n to 1 over poly log n. Afterwards, the direct rounding framework we explained, can run with a k value, which is roughly log n instead of log n. So how do we sparsify very low weight edges? Let's just look at some input graph like this one, and let's just assume for sake of simplicity that the every edge weight is very tiny, say 1 over n. If we run the degree split subroutine on this graph, in the previous algorithm, we only considered the larger edge set output of this degree split, but in fact, it will give us 2 edge sets in a single iteration. But we could run it again and again as long as we want for some k dash iterations, and it will give us some 2 to the k dash different outcomes, which will all satisfy that from in any vertices perspective, they are the same degree. So what I mean is that every vertex will have roughly the same degree in all of these different outcomes and different edge sets EI we generate. And this just proposes a static algorithm. We could just pick the first one, and as a sparsifier, we can just assign a weight 2 to the k dash over n to its edges, and it will be a roughly correct sparsifier. Now, each iteration just requires a pass over the whole edge set. So the whole process runs in n times k dash build time, just like the previous algorithm. And dynamizing it is very, very easy. If roughly epsilon fraction of the edges of the current output we are considering are deleted, we switch to another one. If too many insertions happen in the whole graph, then we just rebuild. And this is all we do. And this will just give us an update time of k dash over epsilon. And combining with the prior framework we mentioned, we get U tilde k log n over epsilon update time with the deterministic algorithm for rounding dynamic fractional matchings. Note that it would be tempting to use this framework to round all the way to integral, but note that here we need to use both the larger and the smaller outcome of these rounding steps, not just the larger one, and this doesn't allow us to go to all the way to integral. So okay, k dash over epsilon update time if we do the roughly trivial thing, but could we use randomization to speed this up? Well, let's just assume that the updates are oblivious to our randomization. That is, we assume that we're working with an oblivious adversary. If we were to pick a random EI here, then it would take roughly m times epsilon updates for the adversary to delete an epsilon fraction of it, as it can sort of just randomly guess which EI we picked. And this logic already gives us an U tilde 1 over epsilon update time algorithm against this weaker notion of oblivious adversaries. And the idea is, could we do some smarter sampling and make this algorithm more robust? And for this, we will use output adapted dynamic subsamplers, which are generalization of dynamic subsamplers which have been studied by others before. We'll define this data structure now. So a dynamic set sampler data structure is a data structure which can support the following three operations. It can initialize, and it just initializes with some size n and a probability vector of size n. It supports a set operation where you can just say change the value of this probability vector. But most importantly, it supports a sample operation where it returns a subset of the numbers between 1 and n, and I is sampled with probability pi independently from the others. And in this paper, we show a supporting lemma, which might be of independent research interest, is that you can construct a dynamic set sampler with essentially optimal running time, that is linear initialization time, constant setting time, and linear sampling time, which functions against an output adaptive adversary. Note that previous implementations were not provably output adaptive. So how do we use this for sparsifying low weight edges? Well, instead of this previous framework, simply just sample our sparsifier using this set sampler. The sampling time will be roughly the same as the size of the sparsifier, and we can just resample after epsilon fraction is deleted, and this will give us an U tilde 1 over epsilon update time algorithm against an output adaptive adversary, at least, showing the strength of this supporting lemma. Right. So let's just take a brief look at our final framework. The very tiny edges with weight less than 1 over epsilon over n square are ignored. From poly epsilon to over poly n, we use a rough sparsification algorithm mentioned here, or variant of this. And then we directly round this fractional matching without ignoring its internal structure to integral using the first algorithm mentioned. And note that there's subtle work here to combine these two algorithms such that their update times don't multiplicatively add up, they just additively work together. So what outcomes will this lead to? We'll get faster algorithms for fully dynamic bipartite matching. The exact terms depend on whether they are randomized or deterministic, but there are multiple factors of epsilon and logs for most cases. We get fast algorithms for decremental matching, and here, due to the structure of these decremental matching algorithms, there's actually no blow up between the fractional algorithm and the integral rounded version using our framework. But do we get something for non-bipartite graphs? For non-bipartite graphs, we also get some supporting results. That is, we can maintain an epsilon approximate maximal matching. An epsilon approximate maximal matching is just a matching which is almost maximal apart from some epsilon fraction of nodes, where maximality is just defined in a way that a matching is maximal if it cannot be extended by any edge. Note that is folklore that an epsilon AMM is 2 plus epsilon approximate. So our supporting result is that we can show fully dynamic epsilon AMM algorithms with update times log n over epsilon cubed for deterministic, log n over epsilon cubed for randomized against adaptive adversary, and 1 over epsilon cubed for randomized against output adaptive adversaries. And prior algorithms all had roughly 1 over epsilon to the fourth and log n update times for adaptive, omega log n update times for adaptive. So roughly the same improvements as for just the rounding frameworks themselves. So I would briefly talk about some relevant open problems here. Of course, if we could come up with faster fractional algorithms for small approximation ratios, our near optimal rounding framework will raise them to optimal in general. So this probably is the most important direction to go on. But it would be also interesting to see extensions of rounding approaches for weighted graphs or non-bipartite graphs. Such algorithms exist, and very recently, I think on this conference itself, there have been algorithms for weighted and non-bipartite graphs. But as a general question, in different models, fractional appears to be as hard as integral. And is this something we can generally say, and can we even generally say it for non-bipartite graphs? Well, thank you for listening, and these are our main results.